So here I'll resume and then I'll do this in case the people that aren't here are watching. So like this is what we had done yesterday, right? And then we added on quadrant two. And again, since it's on YouTube, you'll be able just to pause it. And then here's quadrant three and then quadrant four. So good. Now it's like we're all caught up. The next thing I want to talk to you about are the tangents. And the tangent ratio, as you'll remember, is the opposite over the adjacent. What's interesting, though, is it winds up being the sine divided by the cosine. So um, you know tangent as opposite over adjacent. In this case, you can think of tangent as sine divided by cosine. And if you're interested in me proving that to you, I could go back and remind you yesterday that sine is, remember, sine is opposite over adjacent, but we learned that the adjacent, um, well, no, I'm kind of talking myself in circles here. It's not opposite over adjacent, it's opposite over hypotenuse. What is the hypotenuse always in these unit circle questions? What's the hypotenuse? It's always one. And so that's why um, I don't know if I want to go down this road, but let's for now, since I'm talking in circles, let's have faith. And then if you want, I can go back and do a better job of explaining to you or proving to you that this is a fact. But tangent is sine divided by cosine. Got it? So why do we care? Well, because we should be able to have memorized three things at each of the 16 unit circle locations. So let's get started at 0. So if we want to know the tangent at 0 degrees, then we just do the sine at 0 degrees divided by the cosine at 0 degrees. What's the sine at 0?
0,
What's the cosine?
1,
What's 0 divided by 1?
0.
So let's add to our, and again, there's not really a spot for it here, but let's just add to this and say that the tangent equals 0.
Oh, there's not like a slot to put it.
There isn't a slot for it.
What are those lines for?
The slots are for radians. So like this one's going to be like pi over 6. This one's going to be pi over 4. I just didn't really want to get to those just yet. So save those slots for our radian measurements, okay? Uh, you- Unless you want to use it, and then we can do something else later on. It's up to you. I don't want to micromanage your unit circle. Let's head over to 30 degrees. And again, what I have to understand, and you'll see complete repetition. We're not going to do this 12 times. We're going to do it a couple times, and then we'll look for similarities as we go around the circle, little shortcut ways. But for the first time, when we're going to do the tangent at 30, we absolutely have to think about it as the sine at 30 divided by the cosine at 30. Deal? What's the sine at 30?
1/2.
1/2. What's the cosine at 30?
Root 3.
3 over
Dude,
2.
would we do copy off?
And if we copy dot flop this, it would go from 1/2 divided by that to 1/2 times that. Everybody okay? Class on this level, I probably shouldn't expect any issues with stuff like that. The twos are going to cancel and we're going to be left with 1 over root 3, which if we rationalize the denominator makes it what?
Root 3.
Correct. And so welcome to yet another, say hello to yet another number that you're going to be saying a lot. Already you can see how root 3 over 2 and root 2 over 2 have become a very common part of our vernacular. Well, say hello to root 3 over 3. So root 3 over 3 is the tangent at 30 degrees. So I'm actually just going to write it, and I'm not even going to write tangent equals. I'm just going to kind of put it in purple here off to the side. Okay. And we, like I said, we can remake these over the next couple days. We can come up with like maybe a better template, something a little more user-friendly, more spacious. I don't know. You'll like this next one, and right away you'll see why. If we're going to do tangent at 45 degrees, I mean, I feel like obliged or obligated. I never know the right one of those to use. But if I'm at tangent of 45, what's nice about it is that
Isn't
it's what?
isn't it just gonna be root 2 or 2?
No,
Wait, it's just gonna be this one.
it is just going to be one. And so these, like I warned you about this, these will become your favorites just because it feels so nice that you're in a place where the sine and the cosine are identical. And yes, they are both root 2 over 2, and you divide that by root 2 over 2. But at the end of the day, it's just one. When you divide something by itself, you get one.
Is 60 degrees root 3?
Yeah, it is. So let's do one more. I know. Let's finish 60 and then we'll hop right up there, okay? 60 degrees, and we're almost there. Tangent at 60 degrees will, of course, equal the sine of 60
Mhm.
degrees divided by the cosine of 60 degrees. And now that we have these in our back pocket, it's not like we have to go back and relearn sines and cosines. What's the sine at 60?
Root 3 over 2.
So we're going to put root 3 over 2 over 1/2. And again, if you copy dot flop it, it looks like this: root 3 over 2 times 2 over 1, boom, boom. And we get, again, say hello to someone who you're going to become quite familiar with. Root 3 is sort of the final character. We're going to stay away from secants and cosecants and cotangents, if not forever, at least for a little while. So your cast of characters is now almost entirely complete. All right. So the main players in the game so far, we have yet to meet one guy. But the main cast of characters so far is root 3 over 2, root 2 over 2, 1/2, root 3 over 3, and root 3. Got it? And Sutter's question that he asked is the last guy. And the question he asks is very valid. Like when I get up here to 90 degrees and I'm pointing due north, if I want to find the tangent at 90 degrees, there's a reason right now, if you were to grab your calculator and type in this, you're going to get an error message. And that's because, and when we get to graphing trig functions, you'll see there's actually vertical asymptotes every 180 degrees in the tangent function. There's the first vertical asymptote at 90. There's going to be another one at 270, and then another one at 450, and so on and so forth. And so the reason there's a vertical asymptote is because it doesn't work, right? And as we know, those vertical asymptotes represent places that the graph can't get to. And here, if you try tangent at 90, you're doing sine at 90 divided by cosine at 90, which Houston, we have a problem. 1 divided by 0 is undefined. So our tangent function up there at 90 is undefined. And I don't know if you're comfortable enough yet with this for me to say this and you to nod in agreement, but that's going to happen now again every 180 degrees, because every half turn now, starting there around the unit circle, I'm going to get a cosine value of 0, right? That's going to keep happening. And every time I get a cosine of 0, I get a tangent that can't work. So it's going to keep happening. Now, you know all the characters. So what I'm going to do, I want you to look really closely. This is how I learned this, and I'm a big believer that everyone can learn it if you just memorize this. I'm going to make some serious vandalism, and I'm going to undo it here in just a second. I want you to pay close attention to these big green dots. And what I want you to know about them is that they share relative locations. What I mean by that is, do you see how they're compressed up higher or lower, and they're compressed closer to the y-axis? Those are going to all have the exact same tangent values, except for the signs are going to change. So you can memorize it as like the y-axis huggers are all going to have tangents of root 3, but the sign's going to go positive, negative, because tangent is a ratio of sine divided by cosine. So maybe my brain works different from yours, but that's how I learned to memorize the tangent numbers, is to just remember that they're all root 3s, just the sign goes back and forth. So at 120, it's negative root 3, and we might as well fill in the rest of these. Let's go all the way down to 240. We're back to positive root 3. And then let's head across to the other y-axis hugger, who's going to be negative root 3. And as you can imagine, you know exactly, you've been hanging out with me for years. You know exactly where I'm going with this. I can also now say the same thing about these big red dots. Do you see how they're all x-axis huggers? They're all going to have the same tangent values, which really, you're so smart. It ought to just make sense why that is. You're dividing a half by root 3 over 2 in each of those places. It's just the signs are a little bit different. So
How was it?
It's very moving.
Who's fine?
Josie. Arizona Aztecs. Down there.
Never heard of it.
So it looks like we're a little cramped on real estate over here to the left, but we can all agree that at 150, we're going to have a negative root 3 over 3.
Yep.
And then if we drop down to our next x-axis hugger, we're going to have a root 3 over 3. And then if we cruise all the way across to our last x-axis hugger, we're going to get a negative root 3 over 3. And that leaves us with
The one.
the mid quadrantals, and we love those.
So that the exact same.
Right. Yeah. Because at every one of these mid quadrantals, the 45, 135, so on and so forth, you're constantly dividing something by itself. Again, just the signs are going to flip around. And so over here at one, uh, I'm sorry, I said that wrong. At 45, we've got a positive one. At 135, we jump back to negative one. And we hop down into quadrant three, and it goes back to being a positive one. And then we head down to quadrant four, and we're back to having a negative one. And we did we did forget a couple. I believe we're almost complete, but we don't have a tangent yet at 180. What's our tangent at 180? Again, it's zero, right? Because you're dividing zero by something. Yeah, it's negative, but who cares? Zero doesn't care. Zero divided by anything is just zero. So our tangent over here is zero. And then our tangent down at the bottom is going to be what?
Undefined.
Because it's 180.
Undefined.
It's cool if they all do positive, negative.
Yeah, as I say, I mean, really, it's intimidating at first. When you look at the unit circle, you think, I have to memorize that. And the answer is no. You have to be able to, in your mind, like when I say 150, you have to be able to picture the arm spinning 150 degrees. And the easiest way to think of that is to say, okay, I came up 30 degrees shy of the x-axis, right? And then you immediately have him pegged as an x-axis hugger, and you can see it. Long cosine, short sine, awkward tangent. See that? So you can do these in your head quicker than maybe you think that you can. While we're here and doing this, we're a little bit ahead of what I thought we would be at. Let's do the radians and let's make this official. And this will kind of mark the conclusion of getting this. Maybe we'll have some time. I don't know. So radians are something we're going to need. Seniors, you probably won't get any of this, but juniors, if we have time to do, trig is so useful. Like you can use trig to calculate the like, have you ever driven by those big wind turbines?
How fast?
Yeah, you can like use basic trigonometry to figure out like the speed that you'd be going if you held on to like the end of one of the blades.
Yeah.
But anyways, for measurements in practical use of trigonometry, degrees generally are not a very practical thing to put in. So instead we use radians. And so I hope this doesn't get confusing. It would be a shame to have such a nice cohesive lesson and then blow it here. So let's just talk about a circle in general. You guys know that the distance around a circle is called the circumference. And you guys know that the formula to find the circumference of a circle is 2 pi times radius, more commonly known as pi times diameter, right? We good? So if I wanted to know, now be careful, there's a difference here, and this is where things can get a little confusing. Watch out. Yes, there it is. So just be careful that you start to, and you may be 30 years old and still never understand the difference between the two, but a radial measurement, you're measuring like the portion of the distance around the circle that you traveled, whereas with an angular measurement, it's the same vibe, but you think of it more as how many degrees has the arm spun. So if I were to start,
I don't know if I'm like on the same sheet of music or whatever mentally, but like if the radius of the whole thing is one, wouldn't like 90 degrees be like a 0.25? Or does like go up like a quarter? Or like if it's one circle and it equals one.
the radius being one, you mean?
Yeah.
I do apologize. I don't really think I understand your question.
Like if we're splitting it in quarters, right? By like the 0 degrees, 90 degrees, 180.
Yes, each quadrant is worth pi over 2.
Okay.
Is that what you're asking me?
Yeah.
Interesting question. Yes. I think the best way for me to maybe approach this, to have any shot of this just making complete sense, is this. Watch my green pen. I'm going to start here. What I really want to know is the radial measurement if I travel all the way around this circle. And again, bear in mind, I'm just finding something called the circumference right now. And so if I want to know the length of this green thing all the way back around like this, then I use this formula over here. And as a couple of you have already sort of light bulbed into, the diameter of this circle runs from here to here. How long is it? It's 2 because it takes 2 radii to get from purple X to purple X, right? So if the diameter is 2, then we can officially say that the circumference of the unit circle is exactly 2 pi radians. Got it?
Yes.
You don't have to understand what I just did in order for the rest of this lesson to make sense, but it helps if you can have a little bit of buy-in as to, like, I'm not just saying 2 pi and you're not just going to write down 2 pi. You're going to buy it because the radius is 1. 2 radii make a diameter. Diameter pi makes the circumference. So I'm going to backtrack a lot because I've got a lot of vandalism here now. So what helps to make sense of this is for you to now start. I like to do chunking. When I teach radians, it helps me a lot to chunk. And so the first blank has a 0. I'm going to switch to green, I guess, for this. And I don't know what you want. I don't care what you do, but let's start here. And that's at 0 radians. So 0 degrees and 0 radians are both just effectively someone saying the beginning. Now, the best way for me, I've done this for a lot of years, the best way I can think of to chunk this is let's go all the way back around the circle. So if I go all the way around the circle, 1 full revolution around the circle, I have gone 2 pi. So again, just like that is 0 and also 360 degrees, we also know that point as 0 and 2 pi. Now, the first logical chunk would be to divide the circle in half. And by that, I mean, let's make a half journey. So the artist formerly known as 180 degrees, what do you think we know him as in radians? Pi. Can you see green when I write in green?
Sort of.
Just looking for a color that's different than red and purple.
And you said you don't want decimal points. You only want fractions, right?
Right. We're not going to have a lot of decimals. Listen, decimals are going to come into play when we start talking about practical applications of trigonometry.
Mhm.
There are going to be decimals all over the place, but we don't want any of that right now. And then let's chunk again. So if I now take half of my half journey, the artist formerly known as 90 degrees is what? 1/2 of pi, which we're not going to call 1/2 pi. We're going to call it pi over 2. Same, right?
Yeah.
Now, this is where it gets a little bit tricky. So what I want to do next, and I'm going to really do some heavy duty vandalizing here, and hopefully this vandalizing sticks in your head. I'm going to take the journey from far east to far west, and I'm going to divvy it up into these chunks. 1, 2, 3, 4, 5, 6. When someone finally showed me that was when the first time I went, oh, I see. This is easy. What I want to think about is that each of those chunks is 30 degrees. But from a different perspective, what fractional portion of a pi is it?
0.6 or like a 6.
Fractional. It's exactly 1/6. If you think about it, this entire journey from far right to far left, we already established is 1 pi, correct?
Mhm.
If I can divvy it down into 30, 30, 30, 30, 30, 30, that's exactly 6 chunks. Therefore, that now opens up a whole new world of possibilities for me in understanding radians, because now I can go to my first blank and say, you, sir, are exactly pi over 6. You're 1/6 of the way to pi.
And then would the negative and positive signs be the same deal?
Radians aren't gonna, that's only when we start spinning our angles clockwise. We're not going to go down that road. So the degrees and the radians, we're not going negative just yet. So we're just talking fractional portions of a full spin. So what I want to do at this point is skip 45 degrees. And the reason I say that is because I want to go back to my vandalism. You remember when I had this chunk? We now know that chunk is worth 1 pi over 6, right? If I add another full chunk, sorry, 45, I don't mean to be offensive or rude, but I'm skipping you. If I go to the next awkward angle, it's 2 pi over 6. Don't write that down. Because what does 2 pi's over 6 reduce to?
1/3.
1 pi over 3. So up here now at the artist formerly known as 60 degrees, let's give him his radian name, pi over 3. And let's keep hitting these, and then we'll come back to the mid-quadrantals. But you see, if you chunk it logically, I think it's pretty easy to memorize. Let's add another pi over 3. which gets us up to, of course, 3 pi over 6, which is pi over 2. We've already got that one. Let's head down. Let's do another chunk. This chunk right here. Zoom. What is that? It's how many? Let's see. 1, 2, 3 pi over. It took 4 of those pi over 6s to get there, right?
Uh-huh.
But instead of writing 4 pi over 6, we're going to call him 2 pi over 3. There you go, everybody. Good job. So we've got 2 pi over 3. Let's add another chunk, another journey of 30 degrees, or as we now know, another journey of pi over 6, taking us all the way down to the artist formerly known as 150. What's that going to be? Nailed it. 5 pi over 6. And let's keep on with the 30-degree vibe. Okay, these are the tough ones. And now we're going to go another 30, and that's obviously going to get us to 6 pi over 6, which we've already been there, done that. We know that that's pi. So if I add another pi over 6 to my 6 pi over 6, yes, we get 7 pi over 6. And add another pi over 6. What do you
8
get?
pi over 6.
8 pi over 6,
Which
which is 4 pi over 3. Add another pi over 6, and you now have 9 pi over 6, right? Which is 3 pi over 2. Probably should have filled that one in earlier, but didn't feel like the right time, I guess. So the next one's going to be 10 pi over 6, which we'll reduce to be 5 pi over 3. Good. So again, the artist formerly known as 300 degrees now has a new name, an alter ego, if you will, of 5 pi over 3, which leads us then to the last guy who's 11 pi's over 6, and there's no reducing that. And so we're going to leave 330 as just straight up raw 11 pi over 6. You don't like that one? I love 11 pi over 6. That one always just scratches a certain itch for me. I love it. Let's head to the mid quadrantals now. So let's think about the chunks. And again, that takes 1, 2, 3, 4 journeys of 45 degrees to get to 180, right? So each of those red arcs you should know is a fourth of pi over 4. So these ones should be pretty slick and easy. Not a lot of math to do here. So when I make my first stop at 45 degrees, what is that in radians? Yeah, you guys are pretty amazing. Pi over 4. And then again, if you think, of course, you go to the top and they're like, duh, well, that's 2 pi over 4. But again, we've been there, done that. That's pi over 2. You can come up with that one a lot of different ways. Let's head another. It's 3 pi over 4. So if we're over here at 135, we're now at 3 pi's over 4. And the next one, yes, would be 4 pi over 4, which we've already got that. And add another pi over 4 to 4 pi over 4, and you get 5 pi over 4. And then you jump ahead to 6 pi over 4, which we've already got. And then add one more pi over 4, and you get 7 pi over 4. And there's all 16 of your radian values. Ideally, where we want to be here in the relatively near future is without looking at a written out unit circle. When I say like 7 pi over 6, I want you to immediately get a picture of where it is. And I know that we're a little new in the game for me to say that right now, but there comes a point here relatively soon where you just start to see it. And you don't, I don't know that it's memorization as much as it is like, how does the human brain, when I say to you 7 pi over 6, when I say 7 pi over 6, how do you picture yourself seeing it and getting there? Like, what is your brain telling you? 7 pi over 6. It's a little more than 1 pi.
It's my brain.
Just so if I want 7 pi over 6, I'm going to go to 6 pi over 6, and then how much further do I have to go? That extra one. You start to see that's 210 degrees. I can see exactly where that guy is, right? What about 3 pi over 4? Can you point to it? You see it? Boom, right there. Yep. Perfect. So what happens is over time, it just starts to stick. And we can do it today if you want. I can start awkwardly quizzing you out loud, or we could just be done for the day. We've got everything done that I wanted to get done today. We got our sines, cosines, our tangents, and our radians all filled in. I feel pretty good about that. So, you guys have any questions about that? Prepare tomorrow. I'm going to start rapid fire quizzing you. So I'm going to say things like, Gabe, are you ready? Cosine at pi over 3. Go. Now, you know, code, yeah, don't look at your paper.
I know that.
That's okay. And that's where we're headed. Okay. So you today saying I don't know is to be expected, but starting tomorrow, I'm going to give you some flack, some grief. Does anyone want to test? I can stop recording now, but does anyone want to test their skills? And you have to maintain eye contact, not creepy eye contact, but like I have to know you're not looking at your unit circle. Anyone want to try?
What about people that